and we're going to talk about intermolecular forces. Part of this I skipped, that section 10.8 that I skipped half of. I'm going to talk about that half of it today. And then we're going to, this is 12.6, so that's where you really need to have that information, so I'm bringing it up here. So new slide. And we're going to talk about polarity. And polarity comes from electronegativity. So let's say I have hydrogen bonded to fluorine. Okay, so I have hydrogen bonded to fluorine. So this is what its Lewis structure looks like. And then you look on the periodic table and you ask yourself, which has the higher electronegativity? Okay, so this is at the end of chapter 10. And it's fluorine. Fluorine's electronegativity is 4.0. You took all the periodic tables that were here. Yeah? Oh, in the corner, good. So if you have that yellow periodic table, if you need it, there's some more up here. Look on your periodic table and you'll notice on the fluorine box on the bottom right, it says 4.0. What is it for hydrogen? 2.1. And so electronegativity is the ability of an atom to draw electrons towards itself in a bond. Okay? So when that happens, the way you think about it is the electrons are drawn in this direction. And for many reasons, but the general summary of reasons is because fluorine is small and has a high electron affinity and very high ionization energy, it tends to grab electrons when it bonds. So it pulls the electrons towards itself and creates a situation where the electrons in the bond aren't uniformly distributed anymore. Okay? So let's pretend I had money. I have an expired National Parks pass. That's about all I got. And my mom's credit card because I go do her shopping every week. Okay, so let's pretend this is the pair of electrons. And it's sitting right between us. Okay? Well, one of the electrons is hers, actually, and one electron is mine. And we both have nuclear charge, positive charge in the nucleus. So this is neutral at this point. Okay? Now, if the electrons, what's the charge of electrons?
Negative.
Negative. Let's say, this happens in my house too, the electrons are closer to you than they are to me, right? What happens to her charge? It's no longer neutral, right? Because it was neutral when we were sharing them right in the middle, right? But as the electrons get closer to her, what happens to her charge? She becomes more negative. What happens to me?
Positive.
Yeah, I have less money now. She has more money, right? So like I said, this is how it works in my house with everybody. Like, oh, because there was money on this at one point. Now it's a receipt. And like I said, see, literally, I'm not kidding. That is an expired National Parks pass. I use it, not during summer school. Thank you very much. So I had great aspirations of using it all summer this summer, but somehow I got into this class. It's okay. Yeah, I know, right? And in a way, we're all paying for it. In a good way. It's a very positive thing. It's like childbirth, right? I have no idea what I'm talking about there, but I'm just saying. And they say it's really painful, but worth it afterwards, right? That's what every grandmother says anyways. So, sorry, you can think about that. So, if the electrons are moving in this direction, right, fluorine is I'm hydrogen and the other person's fluorine, right? The electrons are always going towards the fluorine. That side's more negative, and this side's more positive. Okay. This is a dipole. This is what I talked at the very end of the last very end of the last chapter on this subject, or lecture on this subject. And they call it a moment. It's a moment because it's a separation. Oh.
You just want to win your lab run, or?
Yeah, because I don't have the other stuff to do it right now, but I'll do it in lab this afternoon. I'll show the other guys in the morning.
Okay.
Yeah? It's not.
How many do you need?
Just like 3.
Cynthia isn't in here, is she?
Huh?
Cynthia isn't in here.
Cynthia,
She doesn't block this bit too.
no.
Cool.
Maybe a couple.
You want two more?
Yeah, the burned up ones are fine. Ooh, the zebra one. I like that.
Yeah, I want to get a couple. Blue, Dan.
By the way, that just got recorded on my lecture. I'm going to do a little demo with candles later, but I might be able to take a break and run up and get the stuff for it. It's a gas laws demo. Okay, so that's called a dipole. It's called a moment because they're separated in time or space, okay? I don't know, that's what they call it, dipole moment. And they call it a separation of charge. But if you see, that's what it is. It's a separation of charge. That's what that term comes from. And like I talked about North Pole, South Pole, that's also known as a dipole. But it's a magnetic dipole versus an electric dipole or charge-based dipole. Okay, so here's the thing, and this is why it's important in this chapter. Because we're going to be talking about solutions and or solids and liquids, actually, solutions next chapter. It governs, the separation of charge governs the behaviors of solids and liquids. Okay, so if I have a separation of charge like this, okay. Oh, so let's try this. Try this same game, right? I have to get my electrons out. Sorry. Probably shouldn't pull your electrons out in class, I'm just saying. So, now what? So there's a separation, So there's this separation of charge, right? Now she has all the money, okay? If you didn't have money, who would you be attracted to? Would you be attracted to me or to her? Well, her, because she has more money, right? Same thing with charge. If there's a bunch of us sitting around and we all have dipole moments, right? The part of you that has the money is always going to be attracted to or attracting parts that don't have money. Right? So if you take a bunch of molecules like HF and you put them in solution, and so I'm going to, or in the gas, it doesn't really matter. This side's going to be negative. This side's going to be positive. And that's based on the electronegativity, and you got that off the table, right? Another molecule of HF, in fact, many molecules of HF will want to line up like that. You see why? What's the charge that's here? Well, this is negative. This is positive. Has the money, doesn't have the money, right? And so this causes molecules that have separations of charge within them to be attracted to each other. So we call this kind of an attraction an intermolecular force. Intermolecular force because between two molecules, and is created by these separations in charge. Now, it can be a permanent dipole, like this is considered to be a fixed or permanent dipole. Because it's there, it's inherent in the electronic structure of hydrogen and fluorine, okay? But we could also have temporary dipoles, okay? So molecules like Cl2 can have temporary dipoles. So I'm not going to draw the full Lewis structure. I'm going to leave the pairs of electrons on the outside off. But if you look at that molecule, right, what's the electronegativity of chlorine? Well, it's pretty high. It ends up being like 3.0. Okay, look on your table. Make sure you can find 3.0. I could be wrong. It might be 3.0. Right. Oh, okay, good. Because you know what? They changed some of them on me. And I'm pretty sure they changed them. But I could be remembering wrong too. And the older I get, the more of them they change. So think about that. Think about that. Never mind. So 3.0, 3.0. Okay, there is no dipole in that molecule in terms of fixed dipoles, because in terms of electron, right, it's the sharing equally of the electrons exactly in between the two nuclei, so there is no separation of charge there. Okay. On the other hand, the real picture of electrons and atoms is more like this. Like there's these clouds of electrons around each, right? And it's not really a bond. Like we like to think of it as two electrons in between here, but it's actually this cloud of electrons that exists between the two atoms that are bonded. So if I put another Cl here, okay, and that's how it looks right now, okay, what do these electrons do to each other? They repel each other, right? So it is possible then, because what's going to happen when these electrons move? You're going to create a separation of charge simply because it's being repelled by other electrons. So you can create a dipole in a molecule if you can push the electrons around. Okay? You can do that in any molecule that has electrons. What does that mean? Everything. You can do it in atoms too. Atoms have electrons. So it doesn't have to strictly be a molecule. It turns out it's anything that has electron. The electrons can be pushed around and you can create dipoles. And what happens when you have a dipole? Things are attracted to each other. Okay. So I'll talk about that a little bit more, but there's some more details that I need to talk about. This whole concept of a dipole and having a polar molecule, okay, that's what this means up here. Having a dipole equates to having polar molecules. Okay. And this is said to be nonpolar. But it doesn't mean it can't have a dipole. It just means it doesn't normally carry a dipole unless it comes in contact with another molecule, and then that creates a dipole. And we'll talk about that some more. That's more towards the end of this section. Okay, I want to talk about another thing. All right. This takes 3 people. So, you guys are lucky here in the middle, in the front. So let's say we're all bonded together, so we're trigonal planar. And there's a central atom in the middle, right? And we're all fighting over the same money. And we're all the same electronegativity. Where's the charge? It's going to stay right in the middle, right? So even though there's 3 things bonded together, and each of those bonds might be polar, because we're all the same strength, like grabbing onto this and trying to pull it back, that means the molecule will be nonpolar. We're trying to win, but we can't. Okay? So if you take a molecule, this is an exception to the octet rule. I swear I left pens on here last. Here's an exception to the octet rule. Boron with 3 chlorines on it. So you can draw this one out. I don't do a lot of testing on exceptions, but it's for the geometry. So, exception to the octet rule. What is the geometry of this the electronic geometry of this molecule? Well, it's got 3 electron groups, no lone pairs, right? So 3 electron groups. So trigonal planar. It's flat, and it's shaped like this. Now, look at the electronegativity of boron. Get to your periodic table. What's it say it is? 2.0 versus 3.0. Like that. Okay. So is this bond polar? Right, there's a difference in electronegativity. It goes like this. That bond is definitely polar. If you were to just look at this part of the molecule, like this, right, it would be polar. But this one's also the same way, right? Exactly the same, and so is this one. So this is a difficult concept, actually. But if you reduce it down to you're fighting over money, right, and it's the same in all directions, you guys recognize it's still in the middle, right? It's non-polar. These guys are all fighting for the money, right? Great, don't sleep on me. These guys are all fighting for the money, and because none of them can win, it's non-polar because the charge still is evenly distributed around the middle of the molecule. So when you look here, there's some negative, here's some negative, here's some negative, but it's the same. And a dipole means a difference in charge from one end of the molecule, from a molecule to the other. So you can have bonds that are polar, but a molecule that's nonpolar. That's the difficult concept. So how do you know to recognize when a molecule is going to be nonpolar? So let me write this stuff down here. So some rules to figure this out by, okay? Hang on. For a molecule to be polar, first thing that has to be true, it has to have polar bonds. If it doesn't have polar bonds, the way we treat it in here, at least, the molecule is nonpolar. Now, it's kind of like asking this question, we treat it as a true-false statement in a lot of ways in chemistry. We say if it's greater than 0.4, okay? So if you take the electronegativity difference, between the two bonded atoms, sorry, the Wi-Fi is really slow. Bless you-ish. That's kind of a held-in sneeze, so I kind of half blessed it. Is greater than 0.4, not equal to 0.4, but greater than 0.4, then it's polar. Now, the reason I just want to point out, it's not a hard, fast rule. We treat it like, oh yeah, 0.4, that's the number. Okay, your book treats it that way, but it's kind of like gray. What color of gray is that? Well, his shirt, right? The skull dude shirt. It's dark gray. How dark is it? Well, it's darker than that gray. That's kind of how polarity is treated. It's like a difference in electronegativity. It's shades of gray between it is polar and there isn't polar. If it's a lot more than 0.4, it's definitely polar. If it's a lot less than 0.4, it's definitely non-polar. But at the in-between part, it just kind of depends. But that's not a good rule for an introductory class, because it's really done by experimental measurement. So for an introductory class, like this class, it's 0.4. Right? If it's 0.4, then it's not polar. If it's more than 0.4, then it is polar. It doesn't matter if it's, because this is, our electronegativities go to the decimals, some go to the hundredths, okay? So some go to the hundredths of it. And then you can get like 0.04 electronegativity or 0.39 electronegativity differences. And then you're like, is that polar or is it not polar? Right. Well, if you have that table, it doesn't matter because you know better than that to ask the question. Okay, so most must have polar bonds. And then for something to be, a molecule to be polar, it has to be asymmetric. Okay? So symmetry is something that in a lot of ways is taught just by experience, okay? Like the left and right-hand sides of your face are symmetric. This molecule is symmetric in the electronegativity pools. Like the electronegativity pool from boron to chlorine, boron to chlorine, boron to chlorine, are evenly spaced. So that concept of symmetry is very difficult to convey. Turns out asymmetry is not as hard, okay? So if you have one of any atom on the periphery, so let's say it's like this. It's asymmetric. Because the electronegativity difference between here is probably different from here. If it's not, then it's symmetric as far as electronegativity goes, and the molecule will be nonpolar. Okay? The other way, though, that's real common to have a polar molecule, the asymmetry that we're talking about, and this is the one that I just tell people to look for, is a lone pair. Because a lone pair is never going to be symmetric with another lone pair, it turns out. Okay? So if you have one lone pair, two lone pairs, three lone pairs, it doesn't really matter. In all the things that we're studying, it's always asymmetric and polar. Okay? So let's give you some examples. You know what, I'm just not going to put the lone pairs on there for now, because we're only worried about the central atom. Okay, symmetric or asymmetric? Is that? Asymmetric because of the oxygen, right? So that molecule will be polar. The electronegativity difference, by the way, here, this is 3.5, this is 2.5, this is 2.1. So in a way, these bonds are not really polar, but this one is really polar. But it's all pointing in this direction. Okay. The overall charge in the molecule follows this main axis going this way. Okay. Symmetric or asymmetric. I got those two words mixed up. Symmetric or asymmetric. It's actually asymmetric because it has lone pairs, right? That's all you have to look at. The bonds are polar, okay? This is, again, we talked about 2.1 before, 3.5. Okay. So the electronegativity difference is definitely bigger than 0.4. Definitely falls in the class it's polar. The dipole for this molecule points actually in this direction. That's a little bit tricky, but there is a plane of symmetry between the hydrogens, and that's the direction the dipole follows. Let's do this. C. Symmetric or asymmetric? Symmetric. No lone pairs, all the bonds are same. Polar or nonpolar, do you even have to look at the symmetry to determine it? It's 2.4, the difference. 2.1 versus 2.5. The difference is 0.4. So the bonds are already nonpolar. So there isn't a question of whether or not this is polar or nonpolar by symmetry. This guy is nonpolar. So this is 0.4 difference. That's nonpolar. Again, you could come up with other examples. Here's another one, Cl. Let's do CCl4, carbon tetrachloride. And I'm going to leave all the lone pairs off the chlorine because it just takes forever to draw them all. But each one of them has a full set, an octet, okay? And we're looking at the central atom. And carbon's electronegativity is 2.5, and chlorine is polar or nonpolar bond? Polar bonds, but if you look at the molecule, symmetric or asymmetric? What is it, symmetric or asymmetric? Symmetric, no lone pairs, all the bonds are the same, okay? So it's nonpolar. Okay. Molecules like gasoline, or mixtures like gasoline, I should say, are composed of molecules that are like this. But the carbons, you see, those are supposed to be carbons. The carbons can be as many as 18 carbons. So it's a really long molecule. But if you look at this portion of the molecule, it's the carbon bonded to carbon. So is that polar or nonpolar? Nonpolar. Carbon to carbon, nonpolar. And this is carbon to hydrogen. So these are nonpolar. Because electronegativity difference is only 0.4, right? And as a result, substances like gasoline, oils, generally nonpolar. Okay? Water is polar. Okay? And we'll talk about this, actually, subject to the next chapter. So I'll bring it up. I'll have this talk with you again. Generally speaking, substances with different kinds of polarities don't mix. That's why when you take oil and vinegar is mostly water. You shake them and you set them down. What do they normally do? They separate back out, right? So you got to shake it up, and then you pour it on your salad, and then what you end up eating is vinegar with globs of oil in it if you eat too slow.
So how do you, sounds making me think of like oil spills, and like there's a certain type of soap, or some company was saying like what makes it mix? How do you change it? Like what would you do to
Okay.
change
Question is,
polarity?
oil spill, how do you get the oil off the water, or how do you get the oil off of things, right? So it goes down to the molecular nature of soap. Okay, so what I was trying to draw before, this is each one of these is a carbon, okay? And each one of those has hydrogens on it. So this carbon has 3 hydrogens on it. Now I don't want to draw them all because it gets quite painful to draw it. So imagine that each one of these carbons that's up here has 2 hydrogens on it, right? And then I'm not even going to draw the rest of it. It goes like this. We draw them as zigzags, actually. That's our cheater way, so we don't have to draw so much. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be something called nonane. That's the name for it, okay? But looks very nonpolar because it's carbons bonded to carbons and carbons bonded to hydrogens. None of the bonds are polar. So it won't mix with water, right? Old school detergents have, let's see, I'm going to draw the Lewis structure the way you know it. Have things like this on it. I should have added an extra oxygen. Let me just start over. I got too big of a hurry. I don't want to draw it as an exception to the octet rule, but it is an exception to the octet rule. You don't have to, but it looks something like this. And it has a -2 charge on it like that. So this charge, right, polar substances like charged objects like ions. That's why water dissolves salt, for example, okay? So this part of the soap, phosphate-based detergents, right, attracts the water, and this part attracts the oil. So let's say you're a blob of oil. Actually, that's not entirely untrue, but you're also a big blob of water. So, but let's pretend you were just a blob of oil, and I was a soap molecule, right? My nonpolar part would get stuck to you, but my polar part would be on the outside, the charged part. And so what happens is, when you're a blob of oil, the molecules of soap will surround you. And you literally, if you're the blob of oil, then what happens is, it looks like a fur ball from your cat. The negative ends are on the outsides like this. People with cats can appreciate that. You usually find them on the floor with your feet. that looks like that's the fur ball from your cat, but this part will dissolve in water. And so that's how the oil gets pulled out. You can make a detergent to pull it out, or you can do like they have this clay-like material that when you throw it into the oil absorbs into the clay, but it's the same kind of intermolecular kind of attractions. Pulls the clay together, it clumps up and it floats, and then they scoop it off. Okay. Dawn dishwashing detergent turns out to be amazingly good at getting this kind of oil off of animals. Yeah, so they use it. You'll see it all the time. They'll even like have bottles of Dawn. They'll leave them in the pictures because it's really good at that. Yeah. So there's different kinds of soaps, right? There's phosphate-based detergents. We don't tend to use them as much because, anybody know why we don't use phosphate-based detergents anymore? No, it's kind of a weird reason. But it's a very good reason. So phosphate, there's not a lot of free phosphate in nature, so it's one of the things that limits like algae growth. And so if you have phosphate-based detergent and you throw it in water, all of a sudden the phosphate levels are really high and you get these huge algae blooms that will kill everything in a lake. All right, so it's a micronutrient, I guess is the way. That was my understanding of it. It's one of the things that's limiting the growth of like things in a lake. And so when you give it a lot of phosphate, it's like, all right, let's go, guys. And all right. And then nobody has oxygen in the water. What happens when everybody dies? Okay. Okay, so that's intermolecular forces. That's my little talk real quick. Now, so I'm going to go through these slides a little bit more by word for a little bit. I don't usually do that, but you do need to know these things, okay? So intermolecular forces we call electrostatic forces. That means charge separation. Coulomb's law, pluses, opposites attract. That's a lot of different ways we say the same thing. But oppositely charged objects are attracted to each other, okay? And what the intermolecular force strength is determines whether or not it's going to be a solid, a liquid, or a gas. That combined with temperature determine the state of a substance, okay? So, if my intermolecular forces are strong, right, with another molecule, so I'm a molecule now, okay? This is the way chemists think. We make ourselves into things, and we pretend. If I'm a molecule and I have strong intermolecular forces, what's my most likely tendency to do when I'm around other molecules that are like me? Right, strong intermolecular force. Yeah, we're going to be attracted to each other. So we'll hang out like we're buddies. Right? So what do you say, like what's the phrase that people say, oh yeah, I'm really with these people, tight. I'm really tight with these people. It's because their intermolecular forces are so strong, they're always together and they're like a solid or a liquid. Okay? If the intermolecular forces are weak, then they tend to be gases. So when you look at the noble gases, right, these are all monatomic. They're not polar. Because they're not polar, because you can't be polar if you're monatomic. Because to be polar, you have to have two things bonded together. All nonpolar, all weak intermolecular forces, all gases. Because they're not tight with the other molecules. They don't have that intermolecular force of attraction. Nitrogen, oxygen, and fluorine, right? All diatomics, all nonpolar, all gases at room temperature. Okay? Even Cl2. Now, here's something that's interesting, though. Fluorine's a gas. Chlorine's a gas, room temperature. Bromine is a liquid, and iodine is a solid. It's actually a very pretty purple solid. It's like nobody's wearing it, but it's deep, deep purple color. Okay. Do you see the trend? What's the trend? It's more solids down on the periodic table. Now, there's not a nice trend in these, but gas, solid, gas, solid, gas, solid. Okay. Why? I mean, people ask these questions all the time. Why? Right? Well, what do you know about even these? These are all in the same family, and they're all diatomics. What's different about them? Electronegativity is different, but it's all nonpolar, so it's not that part. What else is different about it? AMUs, yeah. And it turns out, the bigger the AMU, right, the stronger the intermolecular forces of attraction. So we'll explain that in a second. But think about it like this. They're heavy, right? They're less likely to be gases, more likely to be solids. Like, hey, right? It's very sedentary, right? You could think of it as a heavy concept. It's not really.
So the diatomics and the monatomics, are they actually polar?
So diatomics, like the ones we're talking about, they're all nonpolar.
But like O2, when it's O1, is it polar and that's why it's
Oh.
O2?
Yeah, it's lacking its octet and needs to satisfy its valence shell. So really, because it has those two unpaired electrons, it really wants to be happy with something. It makes O2 because of that.
And then it becomes nonpolar.
Then it's not polar, yeah. Or it's O2 minus, and like oxide, O2 minus, is like the extreme of polarity because it's an ion that in a bond really just ripped the electrons all the way off. Okay? So strong intermolecular forces tend to result in liquids and solids, which means they have high melting and boiling points, and weak intermolecular forces tend to go with gases. And so we can kind of see that on the periodic table. Okay. So that was the only slide I really wanted to read. Sorry. So I'm going to write some other stuff on here.
So strong molecular forces and the size of the molecules both?
Yeah, we're still going to go through each one of those things, but strong intermolecular force, bigger molecules have stronger intermolecular forces. Okay, so van der Waals, that's how that's pronounced. I know it doesn't look like it. Van der Waals forces, okay? Oh, sorry, I did it with a W. It's a V. That's all dipole-related forces. Now, when two polar molecules are attracted to each other, they call that a dipole-dipole interaction. Okay, so I'm going to just make a new slide because there's just too much going on here. So dipole-related forces, those are van der Waals forces. So you can have this with polar molecules. And we call that dipole-dipole. Because it's the dipole of one molecule attracted to the dipole of another. Okay, so that's where the term dipole-dipole. The other type of van der Waals force is between nonpolar molecules. And that's what I'm going to explain in the next few slides. Like, it's kind of easy to understand. Well, if you have two polar molecules, yeah, they're going to be attracted to each other. But why are two nonpolar molecules attracted to each other? What causes that? That's a little trickier to understand. But nonpolar molecules, remember I said you can have a dipole created within a nonpolar molecule? That's when I drew like the N2, and I said, well, the two electron clouds are next to each other, so it's going to push the electrons in one direction and create a dipole. Anytime you move the electrons around, you're going to create a dipole. So nonpolar molecules have what are called induced dipoles. So polar molecules, that's dipole, dipole. It could be like water. Has a dipole that goes like this, and another water molecule like this. In a lot of ways, it's like they stack because of the dipole interactions, because that's how they line up. So like you have those little Tupperwares in your house, or the, what do they call them, Gladware? Those, the new disposable plastic things, not Tupperware, right? And they're all shaped the same way. It's like that's their dipole, their shape, and you just stack them up, and that's what polar molecules would do. Okay? But induced dipoles come from movement of electrons in the electron cloud. But those are all related to what we call van der Waals forces, forces of attraction. And then I'm going to draw my little nitrogen like this. It's actually triple bonded. Or did Cl2, huh? Could be N2, doesn't matter. And then the electron cloud is not evenly dispersed in that. So that does look evenly dispersed. It's to one side, and that's being caused by a negative charge somewhere else. And that makes those electrons move away, okay? Okay. So here's a bunch of helium atoms. And I almost hate this picture, but we'll stick with it. You don't think about it, but helium has 2 electrons, right? And they're moving around an electron cloud. If you think of them as objects, which you really shouldn't do, but if you think of them as spots, like moving around, right? At any given instance, these dots that are in here can either be evenly distributed or they can be unevenly distributed. So like when it's evenly distributed like this or like this, there really isn't much separation of charge because all the positive and negative are sort of spread as much as you can, okay? But it turns out in an instant that all the electron density could actually be on one side. And when the electron density moves to one side, okay, you have a negative charge on this side and a positive charge on this side. Now helium's the easiest one to explain it with because helium is so small and it has 2 electrons, right? And so when you're going to move the electrons around a helium, you only have to think about 2 of them. But what if it's like iodine or xenon, right? So let me draw to scale here. So here's a helium. And there's an uneven separation of charge. This side becomes negative and this side becomes positive, right? That's the helium atom. The electrons move to one side, so one side's negative, one side's positive. What's that going to cause to happen in this atom? Because there's a positive charge here, these electrons in this electron cloud are now on this side of the molecule because the opposite charges attract each other. And so this guy, by having an uneven distribution in charge, creates an uneven distribution in charge on the next guy. That's the induced dipole. That is, the electrons are moving around, they move to one side, and suddenly I have a pole in the molecule which creates a pole in another molecule. Now, iodine, or let's do a xenon, right? Much bigger. It's got 54 electrons, right? And when the electrons are to one side, it creates a much bigger separation in charge just because it's a lot bigger, right? So I get a much bigger negative on this side and a much bigger positive on this side. And what does that do to the xenon that's next to it? It causes the electrons in this one to shift to this side. And so you get an induced dipole, but it's related, right? to the mass because it's related to the number of electrons and the size of the molecule. The bigger the molecule, the bigger the induced dipole. So in general, as the molar mass goes up of nonpolar substances, the induced dipole goes up. Okay. I'm skipping over a few things. Here's the trend. This is the data. To show how it plays out, like the real world kind of plays out. Okay. So here's helium. Has a molar mass of 4, which, I mean, you can read off periodic table. Its boiling point is 4.2 Kelvin. That is incredibly cold. Right? That's 4 degrees above absolute zero. Neon is 27 degrees Kelvin. Remember, bigger mass, more electrons, bigger induced dipole, or dispersion force is what they call it. Okay. Argon is bigger. Krypton's bigger. Xenon's even bigger. That's 165 Kelvin. Now, those are still all really cold, but that trend is caused by the shifting of electrons in the electron clouds, creating stronger intermolecular forces. You see the same trend with like hydrocarbons, like gasoline, molecules that you would find in gasoline, except for, you know, we could look at C, 1 carbon, 2 carbons, 3 carbons, all the way up to like 20 and 30 and 40 and 50 carbons. And when you're at 40 and 50 carbons, guess what? It's a solid. When you're 1 or 2, that's like methane and ethane, right? It's a gas. So again, intermolecular forces depends a lot on this molecular weight.
I guess 40-50 is a tar, huh?
What's that?
A tar,
Yeah. Or you can even have waxes.
waxes.
Waxes are not truly hydrocarbons, but waxes will easily have like 30 to 40 carbons in them. 2 18-carbon chains, usually. So which hydrocarbon has the higher boiling point? Take a guess. Just look at the formulas and ask yourself. C2H6, right? That's ethane. So this one will have the higher boiling point. You can get that just by looking at the formula for hydrocarbons. It's a heavier molecular weight, higher boiling point.
Boiling point means when it turns to a gas.
Yeah, when it goes from a liquid to a gas to get it to be in the gas state. Higher, and the higher temperature means it has stronger intermolecular forces. Yeah. Okay, hang on. Okay, so here's another comparison. Notice these have the same molecular weight. But if you look at the boiling point, right? We'll talk more about boiling point trends in a second. This one boils at minus 19 degrees Celsius. This one boils at minus 88. This is nonpolar. This is one of the ones I just drew on the board just a second ago. This one we decided was polar, because it has the 1 oxygen, right? And the bond is polar. This is the difference between nonpolar and polar. Okay? So the kinds of intermolecular forces that we're talking about, and we'll go through lots of examples of like the types of properties that we're talking about. The stronger intermolecular force between induced dipoles and permanent dipoles is generally a permanent dipole. Okay. So this molecule, this is formaldehyde. Oops, that was good. This one has dipole-dipole. And for the same molecular weight, this one is nonpolar. So it has an induced dipole. Okay, the induced dipole is weaker. And the reason I say that is because the boiling point for this liquid is much, much lower than for this one. And what that means is when you're boiling it, you're getting it to the gas state, it's a lot easier to turn into a gas. So it requires less energy to separate the molecules. Okay, so those are 2 intermolecular forces so far, right? We talked about dipole-dipole and induced dipole. The third one, for the biology people, is the most important one, okay? And that's called hydrogen bonding. And then I'll come back through from the beginning of the slides. There's a slide much later on. I'm just going to draw a slide. Hydrogen bonding. Hydrogen bonding turned out to be a really bad name. Because it sounds like, well, you just have to be bonded to hydrogen, right? And everything can bond to hydrogen. But it's not. So I'll explain it like this. By definition, to possess hydrogen bonding, you have H bonded to N, or H bonded to O, or H bonded to F. Okay? Now, nitrogen in this molecule, whatever this molecule is up here, right? It will have other things bonded to it, just like this oxygen will. They're not going to be sitting there by themselves. But in order to have hydrogen bonding, you have to have this, okay, situation. And they have to be attracted to a lone pair of electrons somewhere. So what do you think the hydrogen bond is? Well, this side's really positive, this side's really negative, and this side's negative, right? What's the hydrogen bonding part of hydrogen bonding? I ate lunch, I'm okay. You can eat. Huh? That's the hydrogen bond, exactly, it's this. And you will see it in your biology text most of the times as a like dashed line like that. This attraction yes. So she said, oh, DNA? Yeah, like in DNA. In DNA, you have nitrogens, right, with lone pairs, and then hydrogens on nitrogens. That's the situation that gives you hydrogen bonding, okay? You also have it in amino acids, can exist in amino acids. There's certain amino acids. I don't think I can draw from memory the bases for DNA. Let me cheat. Because I'm not the first person to do this. I don't think I have it in the slides later. Oh yeah, here it is. Yeah. It's way down there. Okay. So I don't know if this picture makes sense to you or not. These black ones are carbons. And then these are double bonds. Okay, let me point to it here to get my finger out of the way. So these are double bonds, and these black ones are carbons. The blue ones are nitrogens. So this nitrogen has a hydrogen on it, right? So, and this nitrogen has a lone pair of electrons on it. They don't show it, unfortunately. It's a little bit too artistic for my taste. But there's a pair of electrons there. The hydrogen bond that holds these two together is this. And here's an oxygen, and here's an amine group, a nitrogen with a hydrogen on it. And remember, what are the criteria for hydrogen bonding? You have to have nitrogen, hydrogen, oxygen, hydrogen, or fluorine and hydrogen, and then the lone pair. So it turns out in the bases of DNA, these things fit together the way they do because there's two hydrogen bondings here where this is the hydrogen donor on one side and this is kind of the hydrogen donor on the other side. They fit together like a key. Whereas if the hydrogen was down here on this side and this group was a hydrogen here, it wouldn't fit the same way. So the DNA pattern, when you always say A to T and G to C, right? It fits that way because the shapes of the molecules and the hydrogen bonding is what holds them together. So G, that's this guy down, guanine, right, has an oxygen double bonded to a carbon here. And then again, there's nitrogen and amine. This hydrogen bond exists here. And C bonds to G because there's 3 hydrogen bondings that go on here. If you talk about like bond strength, it's about half the strength for all 3 of these of a standard covalent bond, like a carbon-carbon bond, for example. About 120 kilojoules of energy that holds that together. And you have to remember, right, if you think about the structure of DNA, it's these long strands. They're actually composed of sugar, long strands of sugar with these bases on them that pull the 2 sides together. And when one side matches the other, it's like a whole bunch of keys fitting together going all the way up. So when one of them doesn't fit right, there's a mismatch, right? It's so obvious to like the mechanisms of the DNA that there's a molecule that will come along and recognize the mismatch and cut the wrong one out and put the right one back in. Yeah.
Do we have like birth defects, like because of, chromosome stuff?
Uh-huh.
Because they're not bonding in the way they're supposed to?
Yeah, so that's a tough one. There's different ways that happens. You can have whole chromosomal abnormalities where like a whole arm is like missing, right? Or you can have what are called point mutations. And we get point mutations all the time. That's a single DNA fragment that gets switched out and something else gets switched in. And then it replicates, and so that point mutation stays, okay? The thing is usually when those things happen, they're not in critical components. It's not going to be life or death
It's like
for you.
albino.
Well, no, it'll be like I probably have point mutations, right? But it sure didn't affect me having kids because I have 6 children. And it doesn't show up in my children either because I'm assuming they're all fairly normal. They're my children, but
Also allows
Yeah, so you get these mutations all the time and you carry them along with you. It's only that we notice them when one of them becomes like fatal. And you're like, oh, he died because he had that. And then you think, well, every time I get a mutation, I'm going to die. No, we get mutations all the time.
That's the basis of evolution.
Yeah, genetic variation. So anyways. There's an interesting paper that just came out. And I scratch my head sometimes and wonder, like, what are these people thinking when they write these papers? They found, so they took mummies that were 2,000 to 3,000 years old. So that in the Andes, you find all these shriveled up bodies in caves, right? They took their stomach contents, because they're so well preserved, you can see like what they ate before they died. They take their stomach contents, and then they cultured the bacteria that were in there. And I forget what the percentage is, but you know how we have antibiotic bacteria that are a problem now? They were already present 2,000, 3,000 years ago. So they cultured them and tested them for antibiotic resistance, and they already had it back then, right? So why is that? Well, most of the antibiotics we make come from natural products. They had bacteria in their stomach that had already figured out how to fight that, okay? And then it doesn't necessarily have a benefit to the organism until you try to kill it. And when you go to kill it with an antibiotic, all of a sudden, those are the only ones that survived, and then they're a problem. So we overuse antibiotics. We tried to kill everything, right? But because our antibiotics come from natural sources, it was already present. So we just selected for a large population of antibiotic bacteria. But they were already present 2,000, 3,000 years ago. Anyways, it was a big paper came out, I don't know, just like last week, 2 weeks ago, where they took all these mummies and extracted, this is what I do for my fun, extracted stuff out of their stomachs, cultured the bacteria, and they found out, hey, they already had antibiotic-resistant bacteria in 2,000 years ago, 3,000 years ago, before we had antibiotics, right? Yeah. All right, so back to the very beginning. Back. There's a lot to do in this chapter. See this?
So do the antibiotic, those things in their stomach, bacteria become resistant through their own mutation? Is that how they?
Well, they already had the mutation, so we don't know
So-
how they got the mutation. But they had it at the time that these people died. And then we selected for it. We made it a beneficial property for the bacteria by making antibiotics pervasive everywhere. And so then all the non-resistant bacteria were killed, and only the resistant ones are left. But they were already there in the population. We're talking, you know, when you think about the population of people, and we think, oh, there's a lot of people on the planet. There's way more bacteria, right? Of every strain and type, right?
I heard that there was more bacteria in your gut than you had cells in your body. Is that possible?
I don't think that's possible.
Oh, it's an amazing statistic.
Your stomach would be really big.
I don't know.
Okay, I don't know. I'd have to think about that. Maybe more than there are people in the planet, but I don't know about. Okay, so we're going to talk about intermolecular attractions. Again, that's what this thing is about. And intermolecular forces are really important. They're responsible for lots of things like taste perception, smell. These are all caused by intermolecular forces, okay? Okay. And we don't think about these things, but this is, and so you kind of got an idea of what the intermolecular forces are. They're induced dipole, 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 and hydrogen bonding. Those are the things that we're talking about. And it's the shapes of molecules that make that happen. Just like in DNA, shape and pattern recognition are important in order for your DNA to replicate correctly and not have a bunch of mutations, okay? So it turns out your tongue has receptors on it, and they all have a three-dimensional shape to them. Well, most people's tongues do, not everybody. And your nose has receptors in it. And when you smell certain things, what you're actually smelling, this is the weird thing to think about, is you're smelling the shape and the intermolecular forces of the molecule. And they attach to receptors in your nose. They don't actually go into your tissues, but they fire a nerve and a receptor that your brain interprets as a smell. Okay? So think about this. How many of you know what caraway is? Like rye bread. It's that kind of gnarly, okay? And spearmint. How many of you know what that is? You may not know this, that those two molecules are exactly the same, except one's shaped, like one's like this, and the other one's like this. We literally call it the left and right hand. What that means is you have receptors in your nose that when this goes into your nose, right, you smell it as spearmint, and when the other one goes in, you smell it as caraway. Even though it's just, the only difference is it's a mirror image of each other.
So you smell shapes. You can say.
You smelling, when you're smelling stuff, you're smelling intermolecular forces and shapes of molecules. How's that for being here? And you can say, wow, you smell like a tetrahedron to me. And, you know, if you're hanging out with the right people, they'll be like, ah, you're like trigonal planar. What's that? Yeah, you're part of the small population now that understands that weird kind of humor. Okay, so, also, how many use albuterol, like inhalers? That's a pretty common thing, right? Albuterol inhaler, it turns out for many years they didn't recognize that there was a left and a right-handed version of albuterol as well. Now, one version is a vasodilator, and the other one was thought to be harmless, completely harmless, until they were able to separate the two from each other and recognize that in some people, the other hand was like the bad hand. It actually caused vasoconstriction. So they did a study. Who wants to be the control of this study, right? Where they gave people the mixture of left-handed, right-handed albuterol, and then they took the left-handed version, and then they took the right-handed version, and they treated people in a hospital setting looked at the rates of hospitalization. And when they treated them with just the purified albuterol, which is what you generally get now, the hospitalizations went down dramatically. Because the people that were being affected by this one were ending up getting worse, and the people getting treated by this one getting better. So the shape, again, you're inhaling this stuff's going into your body, it's getting attached to a receptor. And if the shape is one way, it often has one effect. If it's shaped the other way, it doesn't always do this, can have the opposite effect. But it's just the shape of the molecule. They're exactly the same formula. Okay? So these are really important, intermolecular forces and how they interact. So part of this chapter is just getting that point across. Okay, okay, so this is what I like to start with. Just a picture. Let's say these are all the same substance. Okay, so I'm going to paint two pictures. They're going to be completely different pictures, by the way. So these are all represent the same substances. Okay, first, that's the first picture. And then I'm going to redo it. What would you say is different about the three? What? Physical state. But what causes the difference in the physical state? How could you have three different physical states of the same substance? What's that? Closer together, and temperature is what causes them to be far apart. So the difference would be, if it's all the same substance, right, it's temperature. So like for water, low temperature, solid, right, that would be this one over here. In between temperature, like between 0 and 100, this is below 0 degrees Celsius. This is between 0 and 100, you get a liquid state. And then over here, it's high temperature, it's above the boiling point, it's in the vapor state. So this is the high energy state, right? This is the low energy state. Okay, so now erase that picture from your head. I know. I'm taking that variable away from you now. And I'm saying it's different substances at the same temperature. Of course, they all look like they're green balls, but that's okay. Different substances at the same temperature.
Like room temperature.
Yeah, room temperature. Whatever it is right now. What's the difference?
Internal attraction.
Yeah, how strongly attracted the spheres are to each other. Okay? So over here, assuming that the temperature is the energy that's available to them, if it's over here, it's in the gas state. If it's over here, it's in the liquid state, right? So that means these are held together more tightly than these are. So the high intermolecular force is going to be on this side. And I'm going to abbreviate it, IMF. Same abbreviation as what, International Monetary Fund, right? But I'm sure you all think of that. Right? Close together. Why are these close together? Well, they're attracted to each other, right? Why are these ones a solid? Like when we talk about you're tight or you're solid, right? It's because they're really strongly bonded to each other through their intermolecular forces. So if you're now to think about types of intermolecular forces that are available, right? On this side, these are the strong intermolecular forces. That would be things like hydrogen bonding or very high molecular weight.
Crystals.
Oh yeah, and crystal structures. Those are ionic interactions. So the ionic interactions are even stronger than ionic interactions are not technically intermolecular,
It's rocks.
but it's the strongest of the intermolecular forces. Okay.
That's why it's rocks.
And then this is all low intermolecular force. So this is all nonpolar induced dipole stuff that has low molecular weight, basing on what we talked about already. So this kind of transition based on intermolecular forces affects a lot of properties that we want to talk about today. Okay? Do we need a break? 10 minutes? Sorry, I should have asked earlier, but I got kind of carried away. All right, we're going to pause, take a break. We make it work. Okay, so let's talk about gases real quick. You should know some of these just intuitively. It's not saying you should know the list, but you should know some of these intuitively already. Gases have very low densities. Okay, so how low is low? About 1,000 times lower than a liquid. So if we're talking liquids, what's the density of water?
1.
It's 1, right? 1 gram per mil. So 1,000th of a gram per mil is about what a gas is. Okay. We typically, instead of saying 1,000th of a gram per mil, we usually just say 1 gram per liter. So if a liquid is 1 gram per milliliter, a liter is 1,000 times bigger than a milliliter. So we say gases are typically 1 gram per liter. Okay, in that range. So we'll just say 1/1000th of a liquid. Okay, I'll just put that as a little note. They have an indefinite shape. In studying the gas laws chapter, when we talked about kinetic molecular theory, we talked about gases moving in straight lines and bouncing around inside the container. So it turns out a gas occupies whatever shape of container that it's in. So if I were to wear cologne, which I don't, but let's say, maybe I should. But if I were to wear cologne, right, even the person in the back corner laying on the floor could smell it if they were taking a nap. Because the gas molecules of the cologne it's a gas, right? So it fills the entire space of the room. Now, if I were to pour liquid on my head, of course, what would happen to the liquid? It would just all fall to the ground, right? It doesn't fill the space like a gas does. They have indefinite volume, which means can be any size. So you take a small amount of gas, right, and you put it in a flask, or you put the same amount of gas inside a gigantic room, it'll fill either one. Okay, there won't be the same density of molecules, but it'll fill either one. They're very easily compressed because, why are gases easily compressed? Indefinite shape and volume, but they have a lot of space in between the molecules, right? Easy to squeeze together. And their intermolecular forces are very weak relative to the amount of energy in the room or in the situation, okay? Example, carbon dioxide. If you think about carbon dioxide, why is carbon dioxide a gas at room temperature? It looks like this. Bonds are polar, like these bonds are polar, all right? But the molecule symmetry makes it nonpolar. So CO2 is a nonpolar molecule, tends to be gas at room temperature. Okay?
Linear.
It's a linear, yeah, it's linear. And its symmetry shape is linear, yeah. So liquids, higher densities, much higher than gases, again, 1,000 times, right? Indefinite shape. They assume the shape of their container, but their volume is not indefinite. They have a definite size to them. They don't just keep expanding like gases do. Gases will continue to expand until they fill their container. They're also, because the molecules are so close together, very difficult to compress, okay? Intermolecular forces is like Goldilocks and the Three Bears. When she eats the porridge, right? This is it's just right. It's sort of in the middle. There's not a real hard definition for that. It's just modern intermolecular forces relative to how much energy is available. Thermal energy is what they call it, energy. Example, water, H2O. Alcohol, ethyl alcohol, like drinking alcohol, gasoline. Those things are all liquids at room temperature, all have moderate intermolecular forces. Solids, right? High density compared to gases, it's still about 1,000 times. The density to gases is really low. Solids and liquids are about the same. Okay? Every substance, pretty much, that you encounter that goes from the liquid to the solid state is a little bit more dense in the solid state. The notable exception is water. Okay? Water actually expands when it freezes. What does that mean? Same mass, bigger volume, less dense. So that's why, like, when you take an ice cube and you throw it in your swimming pool when you're a kid, thinking it's going to cool it down. I didn't have a swimming pool, I had a ditch. But take an ice cube and you throw it in the water, it doesn't sink to the bottom, right? It floats to the top, and the reason is, right, ice has lower density than water that it's made from. They do have a definite volume and shape. And we talked about this before. They're crystalline or they're amorphous. Crystalline means they're regularly repeating patterns. Amorphous means no regular repeating patterns. And the substances they named as being amorphous are things like glasses, not like glasses, but glass, plastic, wax. Those are all amorphous solids. But they have strong intermolecular forces, and that's why they're in the solid state. And examples would be sugar, salt, flour. And those aren't exactly pure substances, but those are all solids that have tabletops, strong intermolecular forces. Okay? Okay, I'm going to skip over some of this stuff. So, weird thought. If you didn't have intermolecular forces, everything would be in the gas state. Intermolecular forces are what allow us to have solids and liquids. Okay, so two of the properties that we talk about are surface tension and viscosity, and they are a result of attractions of molecules for each other, or intermolecular forces. So what we need to do is define surface tension and define viscosity. So surface, what do we do first? Surface tension, yeah. So, just a general observation. I don't know if you've ever done this before. You should. If you haven't done this, you can do this at home. What does that look like? It's a paper clip. What do you think is in this beaker? It's water. What is the paper clip doing? It's floating on the water. Now, from what you've been told already, right? If something is more dense, and that's made out of like steel, iron, and copper, iron and zinc, and or nickel, and a couple other things mixed together, alloyed together. Isn't that more dense, right, than that? So, but it can still sit on the top. So, anybody go fly fishing ever? Nobody fly fishing? You guys go outside? There's this new app. It's called Pokemon Go, and it makes you go outside. Except for me, I do it for my office. I wait for things to come by. And then I was really lazy. If you guys play this game and you haven't started it yet, going to play but haven't started yet, if you leave the same place 3 times before you get your starter Pokemon, Pikachu shows up. So that's not exciting to you. You're supposed to walk away and come back, but I told somebody what I did. I got in my car and drove away and came back and drove away and came back. I just drove in a circle in a parking lot. And pretty soon Pikachu showed up and I caught him. I parked the car and I caught him. And I showed it to my kids. Hey, I got Pikachu. And they're like, oh. That's the only one I have. I like mostly yesterday. And my dog, my poor dog. Like nobody ever wants to walk the dog. Guess what happens now? I'm going to take the dog for a walk. I'm like, it's like 100 degrees outside. Poor dog. Everybody wants to do, because you know what they're doing? Yeah, they're going to Pokemon Go. All right. I give up. This parenting thing. Okay, so the reason this paperclip is being held up on top of the liquid is what we call surface tension, okay? And surface tension, this is the kind of the weird. Surface tension is the tendency of liquids to minimize their surface area. That is a really not useful definition to me. Okay. But surface tension is the pull of the molecules at the surface for each other, as well as the molecules below. So this is the intermolecular force, the pull of the molecules pulling themselves together that creates a film, essentially, on the surface of molecules trying to attract each other. And because the surface tension of water is really high, okay, when you put a paper clip on top of it, it'll float on the surface. It's not really floating in the sense that we normally think of density-related floating. It's sitting there because you can't break the surface tension. Now, it's really easy to break surface tension. you just add a little soap to it. And one of the purposes of soap is to disrupt surface tension, and that's why it allows you to clean dishes better. Besides getting oil off, it breaks the surface tension, and then the water doesn't beat up as much as it goes into all the dirty nooks and crannies of the food on your plate. Okay, so it won't float on things like gasoline, because gasoline's intermolecular forces are weak, and so the surface film on gasoline's a lot weaker. And alcohol, so like ethyl alcohol, drinking alcohol, or mixtures of alcohol in water, like vodka, which is like a 50% alcohol solution at 100 proof. Okay. When you pour those things, which is messier to pour, gasoline or water, or your experience may be alcohol water. But alcohol water versus gasoline versus water. Which pours better? Like when you're pouring it like this, and think about like some of you may have had the experience of having to siphon gas, and you're trying to pour the gas out of the plastic can. What does it do when it comes out of the plastic can? It comes out the spout and then kind of goes everywhere for a second, right? That's because it has low surface tension, low intermolecular forces. It can't keep the liquid together as it pours out. Whereas water has high intermolecular force, so normally when you pour it, when it comes off the lip of a container, it comes out in a fairly nice stream, okay? Alcohol's the same way if you're pouring pure alcohol in this.
Like, you would have to have a certain amount of water in order for it to float on the surface though, right? Like, because if you just had a little thing.
No, this'll work.
No, if you
as
just
long
had like
as-
a little puddle of water on the table and you put a paper clip, it wouldn't sit on the top.
Try it.
Really?
No, it'll float. But it has to be clean, because if you have any dirt on there that breaks the surface tension up, it'll go straight through. We could try it in lab.
You have to lay it on there a certain way too.
Yeah, you gotta be real careful about putting it down, because you can break the surface tension by dropping it. You know, the really fun place where when you were a kid, I think you were kids, when you were children and you used to play like with water bugs, the water bugs rely on surface tension to get around because they float on the water skaters, right?
Skaters, yes.
Yeah.
It's not because they're so light.
It's not because they're so light, it's a combination of they're really light and it's a combination of surface tension. And when you go fly fishing, this is what I was getting at before, when you go fly fishing, there's a thing called a dry fly. The thing that floats it is little air cells in the hairs that you use for making it, but it's the surface tension that allows it to sit up.
Water moccasins, they're big and they're right on the surface.
Well, they're buoyant though, yeah.
But the lizards that run on water.
Yeah, different story. They're relying on surface tension. They couldn't do that on gasoline. Yeah. But that's another issue. Okay, so surface molecules, okay, these guys experience a net inward pull. This is the very surface of the liquid. These guys experience a pull in all direction. Okay, so think about this. It's uneven here, the way it's pulled down. So if you take a drop, right, and you don't think about this, but when you do a water drop and you let it drop, it kind of looks like a teardrop shaped to you, right? As soon as it breaks away, if you do a high-speed camera shot of it, it collapses into a sphere. If you look at water drops in outer space, this is one of the things, like you want to do experiments in outer space, water drops in outer space are actually perfectly spherical because there's no gravitational, no accelerational forces on them. So we see drops like this. When they break off, they would break off and become spheres. This is a bunch of space shuttle scientists. That's a drop of water, a really big drop of water. But what's the shape? It's a sphere, and that's created by the surface tension pulling it in.
There's no gravity pulling on it.
Yeah, there's no gravity pulling it, but even if there was gravity pulling on it, it was accelerating it. Might elongate as it accelerates, but once the acceleration sort of is constant, it will blob up again.
Could you stick a straw in that and drink it?
You can. That's one of the
That'd
things
be
they
so
did.
cool.
That's, I think, how they made, partially, one of the ways they made those is they took liquid and they pushed it out of a little tube and they formed this bubble. And then, right, this is like a bad thing about it. This is a giant metal can with electronics in it, and this is a giant ball of water, right? The reason the water stays together at all is the intermolecular forces. Keep it together. Okay, so here's the other one, is viscosity. Oh, so, hang on, back up for a second. High intermolecular force, high surface tension. Weak intermolecular force, low surface tension. The other one is viscosity. Okay, so most common place you experience viscosity, the definition is resistance of a liquid to flow. Which sounds, again, it's one of those definitions. Like, okay, pancake syrup, right? You go to make pancakes, or waffles if you don't like pancakes. I like waffles better. And I only thought of that because the waffle maker is out in my house for some reason. So somebody made waffles yesterday, didn't share. And then you pour the syrup, you get it out of the cover and you pour it. What does it do?
Takes forever.
Takes forever to come out because strong intermolecular forces in sugar, okay, the molecules of the sugar and the liquid of the syrup cause it to flow slowly. Because in order for a liquid to flow, molecules have to move past each other. And since they have strong intermolecular forces, they can't flow. So, right, motor oil is more viscous than gasoline because in motor oil you have stronger intermolecular forces. Honey is more viscous than water because, again, honey has these sugar molecules in it that cause strong intermolecular forces in addition to having some water. So you have this dilemma. You made awesome waffles. You have really good syrup, but you can't get it to pour out. How do you solve that problem? Add water. You heat it. Add water to your pancake syrup. That's disgusting.
Oh, I thought you were making it bad.
No, not bad. The syrup, yeah, you warm it up because the increased energy, kinetic energy of the molecules allows them to overcome the intermolecular forces, and then they pour out better. Okay? Yeah, so surface tension and viscosity go together. They're both high when the intermolecular forces are high. They're both low when the intermolecular forces are low. Okay, I'll summarize this in a table when I'm all done. But I just want you to think about the concept. And if you heat the substance, then that lowers viscosity and it lowers surface tension. That's why hot water cleans better than cold water. In addition to dissolving more gel, it has lower viscosity, lower surface tension. Okay?
That's why you can't mix honey into your iced green tea, but you can put it into your hot green tea and it'll...
I guess if you drank green tea. I'm kidding. I do like green tea, but it's like one of those things that I'm like, oh, I should drink that, and then I forget about it. My mom gives it to me all the time. Oh, you should drink green tea. Okay, great. So I got this cabinet full of green tea. Okay. Oh, so this is what I was talking about, right? This is the pancakes. This is the syrup. You see that's piling up on itself because that's the resistance to flow. But you can solve that problem just by heating it up, and it'll flow like water will. Okay. So let me write over here on this side. So surface tension, viscosity. Okay, they go up when the IMF, so does that make sense? It's rising with increasing intermolecular force. Right. This viscosity goes up with increasing intermolecular force too. So the same thing can be true at low intermolecular force, low viscosity, lower molecular force, lower surface tension. The other thing that's true is surface tension, so I'm just going to call ST, and viscosity is called V. They go down when the temperature does that. Okay? Just a code to help you remember. Rather than writing, because we do a lot of increasing, decreasing, higher and lower, having a little code with the arrows. Surface tension and viscosity decrease when you have an increase in temperature. That's what that means. I try to stay fair. It's like reading a sentence, except it's got arrows in it. Okay, so evaporation or vaporization, that's the transition between the liquid and the gas state, okay? Vaporization only happens at the surface of a liquid. Only happens at the surface. The molecules in the inside are sort of trapped in the inside. But stuff on the surface can evaporate. So that means, okay, if you have more surface area, it'll evaporate faster. So like when you're hot and sweaty, you go like this, right? You know what I'm talking about? You guys have all done it. And then it cools down. Because you take the sweat and you smear it out on your head, right? And it creates more surface area for the liquid. And when you fan yourself, that evaporates and it cools you down faster. Okay? So increasing surface area increases the rate of evaporation or vaporization. The other thing you can do to do that is increase temperature. So higher kinetic energy, liquid molecules are held together by intermolecular forces like hydrogen bonding or whatever. It doesn't really matter what it is. But when you increase the temperature, you overcome those intermolecular forces and then they'll go into the gas state. This one you don't get to do, decreasing the strength of intermolecular forces, but in general, lower intermolecular forces, higher rate of evaporation. But you can't take like water and change its intermolecular force. But in comparing two things, intermolecular forces and evaporation go hand in hand. So we're going to call it vaporization, forming of the vapor. Increases with increasing area and increasing temperature. And decreasing intermolecular force. So that, the way I would write that is like this. Things that are easy to vaporize, we call them volatile liquids. That's a very vague thing. But if you pour it in your hand and it feels cold really fast, it's probably a volatile liquid. That's not a good way to do it, but it's evaporating really quickly. Things that don't evaporate are non-volatile. So like if you pour pancake syrup on a plate and you come back 2 hours and hope that it evaporated, no, it's still there, right? Non-volatile. Pancake syrup is very non-volatile because it has such high intermolecular forces, it won't evaporate. On the other hand, if you have a little paint thinner left over and you pour it onto a plate and you come back an hour later, it's gone. Because it's a hydrocarbon, has very low intermolecular forces, so it evaporates very quickly. Probably shouldn't do that, but that's what a lot of people do. Just saying. Okay. So these guys are the ones that can leave. If you have a container that looks like this, they can only leave from this part. If I take the same container and make it really wide, but the same volume, now the surface area is much bigger and it'll evaporate at a higher rate. Okay? So if you look at what's called an evaporative cooler, you know what they call those, like we just call those normally? Just water coolers, swamp coolers, right? What is, you guys know what I'm talking about? Old-fashioned swamp cooler. It has like a sheet of paper on it, right? And they spray water on that. The reason they do that is because when you spray it over the surface like that, you get a really big surface area and then you pull the air through it and it cools by the evaporating of water. It does mean though that the air that comes through on the other side is very humid, very high moisture content. So that's why it always feels a little bit like Freon-based AC feels so much better than a swamp-based cooler, but you know, at some point, cooler is cooler, right? Because it's much less humid. Okay. Let me skip over some of these things. This is kind of a little technical thing I need to sort of mention to you. I almost don't want to talk about this, but I'm going to mention it. If you take 1A, you're going to have to know this. So I have this monster up here. Oh, it's actually full. I really like this one, by the way. But it makes me all crazy, and you don't want to see me crazy. So inside this, it's cool. It's maybe like, I don't know, 15 degrees Celsius cool, okay? Not every molecule in this has the same energy. There's a distribution of energy, okay? And they'll need, in order to leave at that temperature, molecules need to have a certain amount of energy to evaporate, okay? So that thing's cold right now. So what do you know about the rate of just intuitively, what do you know about the rate of evaporation of your monster?
It's not gonna evaporate as quickly as it would if it were hot.
Yeah, it evaporates doesn't evaporate as quickly as if it was hot, right? But the way we think about temperature in science is actually distribution of kinetic energies. Let's say this is the threshold to evaporate, and we say it's cold, that's the low temperature, or it's hot. Really what we're saying is there's going to be more molecules. Not all of them have enough energy. When water is boiling, not all of them have enough energy to leave the solution, but a fraction of them do, and as you increase the temperature, if this graph represents all the molecules in a liquid, it's this fraction that has enough to leave the liquid. And then in a container like that, it's only the ones at the surface that can leave, so it even restricts it even more. Okay, condensation is the opposite of this. I'm not going to get into all the trends on that, but condensation is the opposite of vaporization. Things will condense faster if they have stronger intermolecular forces. Okay. So guess this is, we're going to talk about the basis of vapor pressure now. Here's a beaker, and it's got water in it, right? And clean air. They just emptied out all the molecules on the top. You can't really do that very easily, but let's just pretend we did that. Okay? We introduced the liquid here. At first, it's all in the liquid state, none in the gas state. And what's going to happen eventually is that from the liquid state, they go to the gas state, they begin to fill up the space that's up here. Okay? So this part here, you can only have vaporization. So as a rate of vaporization, molecules begin to evaporate. At some point, you notice how clean the walls are in here, right? At some point, there's going to be liquid rising to the top, gas molecules rising to the top, and there'll be enough of them that they begin to condense. And then what you see on the inside of the container, even though you're not heating it, you see water residue building up on the sides of the container. How did the water get up here? It actually went into the gas state and then began condensing on the sides up here. And at some point, the rate of evaporation and the rate of condensation become the same. Like how much, because you don't constantly have a stream of liquid coming up here, but you have liquid coming out from here, you have it condensing on here, and you also have it leaving from up here. So the rate of vaporization and condensation become the same, and it's that pressure of gas molecules that we call the vapor pressure. It's an equilibrium is the term they use in the slide here. It's a dynamic equilibrium. Oops. Where your evaporation rate and your condensation rate are the same. It's what you see in your shower. Do you like take a shower and all of a sudden you have moisture up on the ceiling? Where'd that moisture come from? Is it because you weren't crazy in the shower? It's because it evaporated off your body and condensed on the ceiling. Right? Or evaporated off the shower head, condensed on the ceiling. Okay, so vapor pressure is the combination of these two things. I'm going to put that up here. Okay, increases with temperature, increases with increasing temperature, and with decreasing intermolecular force. Now, it seems like there's a lot to remember there, but try to remember what each one is and how they would interact with intermolecular forces. And it's not as much memorization as learning principles of how things are working. Okay. Boiling is another property that we're going to cover here. I mentioned some of this the other day. We have something called a boiling point. And remember, I made a graph yesterday. It looks like this. is like pressure and temperature. This curve is actually the vapor pressure curve yesterday that I drew. This is the vapor pressure curve. And I said this is 100 degrees Celsius. And this is 1 atmosphere. So a liquid will boil, okay, when there's enough energy in the molecules of the liquid that they're able to rip the liquid fabric open and create a bubble of gas. So if you have to expand to make that liquid and pull things apart, the strong intermolecular force would tell you what about the boiling temperature. High intermolecular forces require more energy to create a boiling situation because you got to be able to put the bubbles of gas in there. And so boiling point goes up with increasing intermolecular force. It also will go up with increasing external pressure or atmospheric pressure. Talked about that the other day. That's why water in like Colorado will boil at a much lower temperature and affects how long you have to cook stuff. Whereas in the Central Valley, water pretty much boils around 100 degrees Celsius because it's about 1 atmosphere. In fact, today it's almost exactly 1 atmosphere. Okay. I don't have time to do all this. I'm going to start it just to get you the idea. This will be the last slide. So imagine this situation. You have a beaker. And in the beaker you have water. And then you have a flame down here, heat. Okay? So you're heating this beaker. And you start with water that's around room temperature, about 20 degrees. And then you're adding heat energy into it. What happens to it as you add heat energy to it? It gets hot, right? That's how you cook. You heat food up by heating up water a lot of times. So what's happening is you're adding energy down here. Temperature starts low. Temperature increases. Eventually it gets to about 100 degrees Celsius. What happens to water when it starts boiling? Evaporates, right? So when you get to the boiling point of water, now the rate of vaporization is so high that the temperature stops going up. Okay, so you have enough energy in the molecules of water that they want to be in the gas state. And remember, this process from going from the liquid state to the gas state absorbs energy. Okay, so the boiling temperature, this temperature is constant as long as you have liquid going to gas. When the liquid's all gone, then the temperature can rise again. Okay, and then what you're doing is you're heating up the gas. So I'm going to see if this rings any bells. How do you know how much this temperature rises based on the amount of heat that you put in? Rise over run?
Yeah,
Kind of.
Can't you use the y equals mx plus b like you told us yesterday?
Yeah, you did. You know what the y equal mx plus b is? Q is equal to mc delta t. And the intercept's 0. So this is Q is your y, like this is actually your x down here. And to calculate how much the temperature goes up, you can use this equation to calculate how much that temperature goes up. So the temperature change is like this energy from here to here, right? If you know the mass of the specific heat of whatever you're heating, then you can calculate this part here. So you can actually calculate that part of the line, and we're going to do those calculations. But if you see a slope in an increasing temperature, That's a MCAT calculation. So we'll do those. We'll start that first thing tomorrow in lecture, okay? I'm a little behind, guys. So what that generally means on the next exam, I just won't have as much stuff.
Oh,
I know, it's tragic. Huh?
Each question will be worth more points.
But each question's worth more, so you got to get more of them right, in a sense. It ups the ante.